Today we're talking about section 2, which is the quantum model of the atom. And just to kind of take you through time, I have some of the previous developments of the model that we can look at here. You can see that in 1803, John Dalton, remember, Dalton said that the atom was essentially indivisible, and then 1904, Thomson comes along, the cathode ray tube. We knew that there had to be some electrons scattered throughout the atom, and the overall charge had to be positive. So this is where we got our plum pudding model. Then with Rutherford, we realized that the gold foil experiment shows us most of the atom is empty space, so the electrons can't be scattered throughout. They have to be on the outer edges. So we've got this sort of old-fashioned atom you might have seen before, drawn like that in 1911. And then we talked about yesterday, Niels Bohr proposed that the electrons had to be in specific orbitals because of how the light shows off of a hydrogen atom. We see specific energies corresponding to specific frequencies. And now we are going to start talking about how we got to this modern atomic model we think of more as like an electron cloud. So the first person to kind of look at the electrons as a wave was Louis de Broglie. And he noted that the electrons could only exist at certain frequencies, and these frequencies were related to the energies, like that equation we have, E equals hf. And these orbits correspond to those various frequencies. When we watched the Dr. Quantum video, we saw that electrons could be bent like waves or diffracted. If I were to shine a flashlight, if I was standing at home plate on a baseball field, and I shined a flashlight or a laser or some form of light, it's people in left field and people in right field would both be able to see the light because light's able to bend. But something like a baseball, when the batter hits the baseball, you can't hit it to both left and right field, right? It has to go one way or the other. But electrons, which we kind of consider to be tiny, tiny, tiny versions of the baseball, they can be hit to both left and right field, essentially. So because of this, because they have this property of diffraction, specifically through a small opening, is really what we're talking about here. These electron beams can actually interfere with each other, and that's what we see happening when waves overlap. So we get to this Heisenberg uncertainty principle. Werner Heisenberg, a German physicist, proposed that looking at an electron actually knocks it off its course. If you think about it, if you might think that you can see a table in the room or your computer screen, but if I shut the lights completely off, you really wouldn't be able to see anything, right? If there was no light coming from outside, no light coming from the sources inside, you wouldn't be able to see anything with your eyes at that point. And the reason being is because we're not actually seeing the table. We're seeing light reflecting off the table into our eyes. Same with, you see light bending. Something is in the pool. You're not actually seeing the object. You're seeing light bending and then being reflected back to your eyes. So the same goes for electron. The only thing is the electron's so tiny that when we shine a light or use a microscope to shine light at the electron, we actually can move it and change its properties. So if you remember again in the Dr. Quantum video, they said the electron acted as if it was aware it was being watched. That's because as soon as I go to observe it, I change something about it. I add momentum to it. I knock it off course. And it starts to act like a particle. So this Heisenberg uncertainty principle, not the Heisenberg from Breaking Bad, but Werner Heisenberg, states that it's impossible to know both the position and the velocity of an electron at the same time. So this kind of technically, albeit to a small degree, would work with any form of matter because, like I said, in order to observe something, you have to bounce light off of it and change its path. So, I don't know if next time you get pulled over, you want to try that with the cop. Ask them if they know your position, and if they ask them if they know where you are, and if they say yes, then, well, according to Heisenberg, it's impossible to know my speed. So I don't think that's going to get you out of a ticket, though. You can try it, but unlikely. So then we get to Schrodinger. Any of you guys have heard of Schrodinger's Cat before? Maybe. It kind of makes its way into popular references sometimes. Yes. Yeah, you know it in detail. So we'll watch a little video to explain that real quick. Right. No, it's not like a zombie cat.
Austrian physicist Erwin Schrödinger is one of the founders of quantum mechanics, but he's most famous for something he never actually did, a thought experiment involving a cat. He imagined taking a cat and placing it in a sealed box, with a device that had a 50% chance of killing the cat in the next hour. At the end of that hour, he asked, what is the state of the cat? Common sense suggests that the cat is either alive or dead, but Schrödinger pointed out that according to quantum physics, at the instant before the box is opened, the cat is equal parts alive and dead at the same time. It's only when the box is opened that we see a single definite state. Until then, the cat is a blur of probability, half one thing and half the other. This seems absurd, which was Schrödinger's point. He found quantum physics so philosophically disturbing that he abandoned the theory he had helped make, and turned to writing about biology. As absurd as it may seem, though, Schrödinger's cat is very real. In fact, it's essential. If it weren't possible for quantum objects to be in two states at once, the computer you're using to watch this couldn't exist. The quantum phenomenon of superposition is a consequence of the dual particle and wave nature of everything. In order for an object to have a wavelength, it must extend over some region of space, which means it occupies many positions at the same time. The wavelength of an object limited to a small region of space can't be perfectly defined, though, so it exists in many different wavelengths at the same time. We don't see these wave properties for everyday objects because the wavelength decreases as the momentum increases, and a cat is relatively big and heavy. If we took a single atom and blew it up to the size of the solar system, the wavelength of a cat running from a physicist would be as small as an atom within that solar system. That's far too small to detect, so we'll never see wave behavior from a cat. A tiny particle like an electron, though, can show dramatic evidence of its dual nature. If we shoot electrons, one at a time, at a set of two narrow slits cut in a barrier, each electron on the far side is detected at a single place at a specific instant, like a particle. But if you repeat this experiment many times, keeping track of all the individual detections, you'll see them trace out a pattern that's characteristic of wave behavior, a set of stripes, regions with many electrons separated by regions where there are none at all. Block one of the slits and the stripes go away. This shows that the pattern is a result of each electron going through both slits at the same time. A single electron isn't choosing to go left or right, but left and right simultaneously. This superposition of states also leads to modern technology. An electron near the nucleus of an atom exists in a spread-out wave-like orbit. bring two atoms close together, and the electrons don't need to choose just one atom, but are shared between them. This is how some chemical bonds form. An electron in a molecule isn't on just atom A or atom B, but A plus B. As you add more atoms, the electrons spread out more, shared between vast numbers of atoms at the same time. The electrons in a solid aren't bound to a particular atom, but shared among all of them, extending over a large range of space. This gigantic superposition of states determines the ways electrons move through the material, whether it's a conductor, or an insulator, or a semiconductor. Understanding how electrons are shared among atoms allows us to precisely control the properties of semiconductor materials like silicon. Combining different semiconductors in the right way allows us to make transistors on a tiny scale, millions on a single computer chip. Those chips and their spread out electrons power the computer you're using to watch this video. An old joke says that the internet exists to allow the sharing of cat videos. At a very deep level, though, the internet owes its existence to an Austrian physicist and his imaginary cat.
So that's the idea behind the Schrodinger's cat, is that electrons, we don't know exactly where they are, but we can use math to kind of pin down the probability of where they could be. That's why we say this modern model is more like a cloud, because there's areas where it's very, very likely to be the electron, and then there's areas where, as you get further away from that spot, the electron is less likely to be. So it's very fuzzy. It's like a cloud. We're not sure exactly where it is at any given point in time, but we can say it's likely to be here, it's likely to be here, it's not likely to be here. And that's the mathematical quantum theory that describes that. So what we did do with this is now we know that the atom is not really like the solar system. It doesn't travel in those neat orbits around the nucleus. Instead, they're in these shapes, these odd shapes we're going to look at called orbitals, which is literally just a three-dimensional region around the nucleus. It indicates the probability of where that electron is located. So what these numbers we're going to look at do is they tell us kind of the address of where the electron is most likely to be located. So just like if you were in college, there's a chance you're at the cafeteria, there's a chance you're at your dorm room, there's a chance you're at the library. All these are going to have different probabilities. We might not be able to pin you down at one point, but we can sort of address where you should be in relative to your dorm. And I'm going to use that dorm analogy again here. Think of, everyone might go to a different school in a different state, but you can sort of use the state to narrow it down, and then you talk about the specific school, and then you talk about the specific building at the specific school, and then you can talk about a specific room in that building. And most dorms allow two people. That's why I use the dorm example. When we look at these orbitals, every specific orbital is only going to allow two electrons. So the first number that defines where it is, you might have learned about this in middle school, is the principal quantum number. We're going to use the symbol N to denote that. But this is the main energy level. Does it ring a bell if I say that the first energy level can hold 2 electrons, the second one can hold 8? Remember any more than that? Third one can hold. So 8 as well, and then 18 total. I'm not sure if you say 8 too or 8 as well. Yeah. Yeah, so it's 2, 8, 8. So now we're at a total of 18. And the next one is 32. That's okay. 32. And you'll kind of see where those numbers come from a little bit more in this chapter. So that's your main energy level. the angular momentum quantum number, this tells me the shape of the orbital. So these are going to be my different shapes. And these shapes can be oriented in different ways. So I have this water bottle here. It could be sideways. It could be up and down. It could be in and out of the screen. The magnetic quantum number tells me what direction that shape is oriented. And then finally, the spin quantum number. It's not a charge, but it has two possible values that we just call positive and negative. Honestly, when we represent these with arrows, we're going to use up and down. But there's just two possible spin states. So that's the point where we've located the dorm room of the person, and there's two people in there. This is just the way to distinguish between the two people. So maybe a student ID number to tell me which one's which. So here are the shapes of the orbitals. And there's actually one more letter we're not going to talk about right here. But notice the real simple one is in blue. It's the s orbital. It's actually quite close to what Bohr proposed about the hydrogen atom. It's just a sphere, a simple sphere. So you've got the nucleus, and then you've got your sphere surrounding the nucleus. That's the very simplest energy level, the s orbital. Now the p orbital, a lot of books say this is shaped like a dumbbell. I think I try to say like peanut because I think it starts with P, and I think it kind of is shaped like that a little bit. But it's almost like two balloons that are attached. The d orbital is going to be more like four balloons attached at the center. Except notice there is an odd shape. The fifth d orbital is shaped differently. But notice how there are three p orbitals. Like I said with the water bottle, it can either be going left and right, up and down, or in and out of your screen. So there's three possible orientations there. And then the d orbital has five possible orientations to the point where it even can change shape. The f orbital gets even more complex. We'll look at that a little bit tomorrow. But I do want to focus on this this table. We'll sort of break it down one side at a time. Now notice I have the principal energy level is 1, 2, and 3. And the sublevels available, when I'm in the first level, there's only one available. When I'm in the second level, now I have two available, S and P. And then in the third energy level, I've got S, P, and D. So you've got kind of the exclusive, maybe the exclusive dorm building, and then you have, as we go up in number, more and more people are allowed in each dorm building. And then the S and P kind of represent the type of room. You might be able to get an S room, or an S or a P room, or a D room. But building 1 only has the S-type room, whereas building 2 has S and P, building 3 has S, P, and D type rooms. So in S, there's only one style, one possibility of room, but P has 3 different room styles. So in building 2, I've got 4 total possibilities for a room. And then in the third energy level, I've got the S and the P, and then I add an additional 5 types of room for D. And this is where we get our 2, our 8, and then the total possible electrons in level 3 is going to be 18. If you look at the periodic table, it actually corresponds pretty nicely with that. As we'll see, we have the first row corresponds to the first energy level, the second row corresponds to the second energy level, and the third one corresponds to the third energy level. As we go up, Notice with 4, I have the F possibility there. With 7 different types, so that means it can hold a total of 14 electrons, and add them all together, I can get 32. So remember, each room can hold up to 2 electrons. So it keeps going, 5, 6. The highest we go is 7, but we don't have. We don't have a need for that G and H sublevel because there just aren't enough elements to fill. Once we get up to like the 7 Fs, we've pretty much filled all the orbitals, and we don't need to go any further than that. So G is more of a theoretical idea. Same with H. So that's a lot of information I just threw at you. Is there anything that you would like clarified, or? Because I do want to talk about this one question here. We have what's called the 3p sublevel, which would be the third energy level with the p sublevel. So notice how many orbital types are in that p sublevel. There's 3, and how many electrons can that hold total? 6, because each one is going to hold 2. So this one's asking, though, what's the maximum number of unpaired electrons? So how many? Yeah, 3, because otherwise, if everybody had a pair, there'd be 6, but I can fit, if I put one person in each room, so to speak, I would have 3. Good stuff. I thought that was going to be difficult, but you guys got it. So what's the maximum number of electrons that can occupy a 3s orbital? So in this case, we're talking, we've got 3, we've got s.
Would it be 2?
Yep, because s can only hold 2. Now remember, p has 3 different types, so a p orbital can hold 6 electrons. This stuff tends to confuse people at first, but the more we look at it, the better I think it's going to, I hope it makes a little bit more sense. This is our first 30 orbitals. We got a lot of orbitals listed up here. Notice how it's just broken down, energy level 1, 2, 3, 4. I get to add one more type of room in each energy level. So the first one only has 0. That's basically my S. So this is S. 2 can have S and P. 3 can have S, P, and D. 4 can have S, P, D, and F. Notice every time I have only S, I can only have one possible number there. But when I have a P orbital, the 1 here, I can have 3 different types. So that's my -1, my 0, and my 1. When I expand to 2, I can go 5 types. And then when I expand to 3, I can have 7 types. The numbers aren't as important. We're going to learn how to build these in order of their energy and how to basically know where any electron is on the periodic table. But here are the names of all the orbitals: 1s, 2s, 2p, 3s. It goes main energy level, followed by the sublevel. And then every s orbital has 1, every p orbital has 3, every d orbital has 5, meaning d orbitals can hold 10 electrons, s orbitals can hold 2 electrons, p orbitals can hold 6, and then f orbitals can actually hold 14 electrons. So keep that in mind. There's no homework tonight, but we will look at these electron configurations tomorrow.